Imagine diving into the world of neural networks, where machines possess the mind-boggling ability to learn almost anything. It's like witnessing a whole new dimension of intelligence unfold before your eyes. How is this possible, you ask? Well, it all comes down to their remarkable nature as universal function approximators. This is no ordinary capability. It's on par with the importance of functions themselves, those powerful tools that help us describe and comprehend the world around us. Welcome to Quantum Intelligence, where the impossible becomes possible, and where together we unravel the secrets of the universe. Let's shape the future, one quantum leap at a time. Functions are more than just abstract mathematical concepts. They are the key to understanding the intricate relationships that govern our reality. Think about it. Everything, from the way sound waves hit your eardrums to the light dancing in front of your eyes, can be described by functions. They allow us to model and make sense of the complexity that surrounds us. As we explore various branches of mathematics, we uncover different types of functions, each contributing to our ever-expanding knowledge of the world. Now, let's shift our focus to the exciting world of artificial intelligence, AI. AI aims to create programs that can truly grasp, predict, and model our universe. And to accomplish this, we need AI to construct its own functions. That's where function approximation comes into play. Neural networks step in as the architects of these functions, working tirelessly to approximate and understand complex relationships. In this video, we'll build upon the concepts we introduced earlier and delve deep into the fascinating process of neural networks as they masterfully learn intricate shapes in uncharted territories. Join us on this exploration as we unravel the challenges, limitations, and alternative approaches within the realms of machine learning and mathematics. Here's a quick recap. Functions are like systems that decipher relationships through input and output pairs. But with neural networks, things get a bit trickier. We don't have the luxury of knowing the exact definition of the function we're dealing with. Instead, we have a dataset of input-output pairs. Our task is to approximate a function that fits these data points, allowing us to predict outputs for new inputs. This process, my friend, is known as curve fitting. Now picture yourself observing an actual neural network in action. It's like witnessing magic unfold. The network tirelessly attempts to fit a curve to the data points it's given, and as it learns, it skillfully adjusts and aligns the curve with the data set. This process is incredibly versatile, making neural networks the ultimate universal function approximators. They can adapt to fit any data set, paving the way for limitless possibilities. But what exactly makes up a neural network? Think of it as a powerful, interconnected web of functions. The architecture we're discussing here is a fully connected feed-forward network. Its inputs, or features, and outputs, or predictions, are represented as arrays of numbers called vectors. Within this network, individual neurons perform simple tasks. They take in multiple inputs, multiply each input by its weight, and sum all these values together, adding a bias term into the mix. The math behind this may seem daunting, but we can simplify it. Inputs are gathered into a vector, including an extra value for the bias. The weights are stored in another vector. When we take their dot product, we get the weighted sum. An activation function, like the rectified linear unit, ReLU, processes this sum, determining the output of the neuron. Each neuron holds a piece of the puzzle, gradually learning specific aspects of the function. And when we combine many neurons, we can construct intricate functions capable of modeling complex relationships. The network's weights, those magical numbers, are discovered through a training process where inputs are repeatedly presented to the network, aiming to minimize the error between predicted and actual outputs. Now let's venture into higher dimensions. Imagine the challenge of teaching a network to understand images. Each pixel's row and column coordinates become the input, while the pixel value becomes the output. To tackle this, we extend the concepts of neurons and layers. Yes, it slows down the learning process, but the principles remain the same. And what happens when we encounter parametric surfaces, like spheres? Neural networks strive to fit the surface to the given data points, adapting as they go. But when we encounter more complex shapes, like intricate spiral shells, things become trickier. This is where the limitations of neural networks begin to reveal themselves. But here's some exciting news. Function approximation goes beyond just neural networks. Let's talk about the Taylor series. It's like a magical infinite sum of polynomial functions that approximate other functions around a specific point. Fascinating, isn't it? Each term in the series has a coefficient that determines its influence. So, when it comes to function approximation, the Taylor series offers unique insights and serves as an alternative to neural networks. And there's more. The Fourier series, composed of sine and cosine terms, is another approach to approximating functions. Each term is multiplied by a coefficient that determines its contribution. While it may not be as versatile as neural networks, the Fourier series has its own advantages and opens up new doors for function approximation. Now, let's bring all these methods to life and apply them to a real-world problem: the Mandelbrot set. By observing their strengths and weaknesses in this context, we can gain a deeper understanding of their potential. For instance, Fourier features, derived from the Fourier series, significantly enhance the accuracy of approximation, showcasing their power and usefulness. So, how do these concepts translate into real-world challenges? Let's bridge the gap between theory and practical applications by turning to the MNIST dataset of handwritten digits. Neural networks shine in this space, thanks to their ability to handle high-dimensional data with finesse. While alternative approaches like Fourier features can provide some help in approximation, the complexity of implementation often outweighs the marginal advantage they offer. As we wrap up, let's reflect on the pivotal role function approximation plays in the world of neural networks and other mathematical tools. This video, while exploring fascinating toy problems, serves a greater purpose: to inspire new perspectives and methods that will shape the future. The universality of function approximation unleashes a realm of endless possibilities, guiding us to conquer new challenges and push the boundaries of AI and mathematics. It's an ever-evolving journey, one where we continuously adapt our methods to unearth the secrets hidden within the intricacies of each problem. So, my fellow adventurers, let's embark on this extraordinary quest together and unlock the future with the power of function approximation. If you enjoyed this video and found it informative, please give it a thumbs up and don't forget to subscribe to our channel. By doing so, you'll stay up to date with all the latest news and updates in the field of artificial intelligence. And hit that bell icon to be notified whenever we post something new. Thank you for joining me on this thrilling exploration into the frontiers of technology. Until next time, keep dreaming big and embracing the limitless possibilities of the future.